Hello everyone! Today we're going to dive into the wonderful world of geometry. Let's get started. Some of you may not know how Fibonacci and his numbers actually came about. You know the numbers 1, 1, 2, 3, 5. But what you may not know is that Fibonacci, or Creepinacci as you might call him, was actually studying rabbits reproduce. That's correct, he was studying rabbits reproduce. He noticed a sequence that seemed to grow in a fashion similar to the amount of rabbits, and so the Fibonacci sequence was born. Now, why do we care about Fibonacci and his rabbit obsession? First, we should take a look at the golden ratio. The golden ratio is denoted by the Greek letter phi. Its value is irrational, and we like to say it's close to 1.618. This ratio can be used to form golden rectangles, which are believed to be the most appealing rectangle to the human eye, and they're found all over in architecture, geometry, and in nature. Let's have a look at this woman's face. Let's try and spot a few golden rectangles in her face. The ratio between her eye width and the length of her nose is said to be golden because of the golden rectangle formed. Let's look for a few more. The distance from the center of her lip to her nose, and then the width of her nose, also forms a golden rectangle. The frame of her face is golden, her lip and nose form a golden rectangle, her eye forms a golden rectangle, her nose forms a golden rectangle, her nose bridge would also form a golden rectangle, and then her face forms a golden rectangle. Here we have a few golden rectangles over Aaron Paul. But also note the spirals. These are logarithmic spirals, and more specifically they're golden spirals. Golden spirals can be observed in many parts of nature, such as fractal broccoli, or a chambered nautilus. These spirals are said to be golden because of the golden rectangles used to obtain its shape. So how do these rectangles go back to Fibonacci and his rabbits? If you look at the Fibonacci sequence and divide any number in the sequence by its predecessor, you'll get a golden-like number. The further into the sequence you go, the closer you are to the golden ratio. Another great application for geometry is in geography and engineering. So let's suppose someone wanted to build a bridge over a pond. How would they know how long to make the bridge? The pond is too wide to measure. If we construct a triangle and measure the short legs, we can use the Pythagorean theorem to find the distance across the pond. The Pythagorean theorem shows the relationship between the sides in a right triangle. Now I'm sure you're all aware that a squared plus b squared is equal to c squared, which is what the Pythagorean theorem is. If we input our values and do a little bit of algebra, we find that c, the distance across the pond, should be 17 feet. Now, how do we know the Pythagorean theorem really works? First we construct a square and embed 4 identical triangles inside of it. The short sides of these triangles are A, and the long sides are B, and C is the hypotenuse. So now we know that these two gray areas are A squared and B squared, respectively. So if the Pythagorean theorem is correct, after we add those two areas together, we should have C squared. Let's rearrange this a bit. The hypotenuses of the triangles are now all facing inside. Therefore, the big square is now equal to c squared. And the gray area is what we have left over for, which means that a squared plus b squared is c squared. Let's look at one more geographic example for geometry. This is a map of New York City. As every hospital in the city is a red dot. If we construct what's known as a Voronoi diagram and pick any zone formed, we would know where the nearest hospital is. If you were planning to open a new hospital, where would be the optimal position? Using the vertexes on the graph, we try and draw the largest circle that does not already touch a hospital. And now we can see what finale I want to cover geometry and computing, because that's my area of specialization. Imagine you're building a video game, and you need to move a character across the screen. Because the computer doesn't know how to move things on its own, we teach it using trigonometric equations. We can examine the change in the y values, and then apply those changes with another equation. We can follow with a similar approach for the x values. This is highly related to another geometric topic called a vector. The last thing I wanted to cover with you was, drum roll please, da-da-da-da, a graph. This is not a Cartesian graph, but a data or state graph. In a computer, we use this to represent what state a machine is in. Now, I've defined some variables for us to use, and also some rules on the graph. We can use this graph now to determine if an inputted number is even or odd. Watch carefully, we're only going to do this once. The red arrow indicates which digit is our current input, and the red circle indicates our state. So the machine starts and we move into the current state. We then read the 1 and we follow the path up to S1, because that's what the rule says. And we again read another 1 and we follow the loopback rule. Now, just a note, these rules are read as I is an element of O, so that is the next input is an element of these odd digits we've defined over on our variable side. So every time we read one of these, we're going to move based on those rules. 1 is also an odd number, so we move back to S1. 2 is read now, and we move to S2 because that's an even number. 4 is also an even number. And the last character is the end of input symbol, which is going to be I equals the null. So we're going to follow that out to E. And if you end up in E on this graph, that means you're looking at an even number. If the state died, say, back here, then that would mean we were looking at an odd number the whole time. Or back here, even. Thanks for watching. I really hope you learned something new, and mostly I hope I've given you a different perspective on geometry. Don't forget to like and subscribe.